Hello everybody, good morning. My name is Rory Heslin. I'm an electrical engineer. I'm here with Robin Hall, who's also an electrical engineer, and William Guo, who's a computer engineer. We are Team TSR Grow, and we have been working on the project Automated Spectral Data Acquisition and Analyzer under the technical direction of Mikhail Segal. Do I need to do anything? No. Thank you. Sorry about that. Okay, so TSR Grow. What is TSR Grow, you might ask? Well, TSR Grow is plant growth and lighting solutions. TSR Grow provides full spectrum remote power LED lighting for greenhouses. TSR Grow provides power management and distributed lighting control and environmental monitoring and control. This includes a complete grow management and monitoring system. So some of the project motivations that we had: we would like to automate the data collection. We want to eliminate human interaction during this testing, and we would like to set a standard methodology for this testing. As you can see right here, this is one of the fixtures that TSR Grow produces. This is their biggest fixture. So what are some of the broader implications? We figured there are quite a few. First, we would like to reduce the current test time, already stated. We would like faster and more accurate data with repeatable accuracy. This, in turn, saves TSR Grow money, and we could set an industry standard in this booming industry. So some of our best anticipated outcomes, we have three. First one would be to automate our data collection. We would like to use robotics to collect the PPF, which is photosynthetic photon flux, and PPFD, photosynthetic photon flux density, using a photosynthetically active radiation, or PAR, light sensor. You can see right here some of the data that one of these light sensors would give you. Next, we would like to have a mount for our fixtures. We're testing multiple fixtures, and the construction for this frame must have accurate data collection over varying areas. We need to measure these lights anywhere from a height of 6 inches all the way up to 72 inches. So it has to be pretty modular. Lastly, we would like to have a graphical user interface. This would be an application that would aggregate, sort, and store our information. And the data that we collect must be easily manufactured into these lighting reports. Right here is one of these lighting reports, or you could say a heat map of an array of LED fixtures from TSR Grow. Now I will hand this off to Robin.
So this is how TSR is currently testing their LED fixtures. As you can see here, the light that Roy mentioned is suspended above a rather cluttered workspace by 4 individual cords. Now, underneath are hand-drawn dots on the ground. A TSR employee has to take the sensor, hold it at each point, wait for it to collect the data, move to the next one, and so on and so forth, and then do that at varying heights. What we would like to do is completely automate the system. We will use a robot to carry the PAR sensor across a predefined grid. Each red point is where the sensor will stop, take a reading, and then move to the next one. Above it is our mounting fixture. This will securely lift the light to the desired heights that need to be tested. So far, we have chosen the PLA30 as our PAR sensor of choice. Produced by Everfine, this sensor will collect photosynthetic photon flux density, relative spectral power distribution, and its data can be exported as an XLR JPEG, which, as Rory said, is crucial for the lighting reports produced by the company. It also takes data in a spectral range of 350 nanometers to 800 nanometers. As you can see here, this is where a plant has a photosynthetic response, obviously the critical part for TSR Grow. Finally, this sensor communicates via Wi-Fi and Bluetooth, a critical component of our robotics approach, and costs around $1,300, which was 65% of our budget. We produced the robot that will carry the PAR sensor around the predefined grid. Where the Arduino is currently sitting is where the PAR sensor will go, and the infrared line sensor and a color sensor will follow the line and stop at the sensor points. This is a close-up example of a line that can be followed by our robot. The red points, again, are where the robot will know to stop and take the sensor data. This, again, shows our final product. This hand-drawn animation indicates just how difficult our project is, not each part individually, but the whole. We have to have communication and coordination between the robot, the sensor array, the sensor on top of the robot, and the lighting fixture in order to achieve our best anticipated outcome. And that's why TSR gave this project to us. They value it, and it's something that will improve their company.
So another key accomplishment that we have fulfilled is our design of vertical movement in our lighting fixtures. We were given a predefined space to hang different LED lights off of the ceiling, and our goal is to overcome constraints such as limited ceiling height and concerns on fixture stability. As you can see in the CAD drawing here, our design consists of 4 linear rails attached to our LED lights. We used a simple box to represent our lights, and on each end of the fixture, we've attached a linear rail, and we also fixed the guide of the system. This design will provide us the stability that we need and also creates a uniform movement going up, which reduces the possibility of the light swaying. However, the guide system does not provide any movement on its own, so we will be implementing a pulley system to provide the fixture the lift that we need. We've also built a demonstration model of this design, so feel free to come by our booth to check this out. Next up for the future and the remaining challenges of our project. For next semester, we will be testing our multicolored line following robot and testing our PAR sensor to assess timing of data collection. We would also like to build a standardized line pathway for our robot, build a linear rail mounting system, and if time allows, we would like to improve our robot in areas such as battery life. We want to build a longer battery life or develop a charging station for our robot. The biggest remaining challenge is setting up a wireless communication between the Arduino board, the PC, and the sensor device. The Arduino board, which is used to control the robot, needs to be able to communicate to the PC updated robotic status when the robot has arrived at a data point location, therefore take a data point measurement. The PC needs to be able to handle data collected by the sensor. It also needs to be able to monitor robot status and also tell the sensor when to trigger a measurement. Lastly, the sensor needs to be able to successfully take the measurement and transfer it to the PC before the robot moves on to the next data point location. And we would like to thank everyone who has supported us in making this project possible. Thank you.